Hey guys, this video is to teach you how to interconvert between grams and number of particles. Here, we're going to have to learn how to do two-step conversions. Because notice that in this title, grams and particles, neither of these contain the word moles. And when you're interconverting between grams and number of atoms, or grams and number of molecules, you have to go through moles. So this is actually going to be a two-step conversion. Let's say you have 2.6 grams of carbon atoms. And you want to know how many atoms of carbon that actually represents. We set up our conversion table, but this time we're going to have to go through more than one step. We want to use our grams to mole conversion, which we get on the periodic table, to convert our grams first to moles. And then, in our second step, we're going to take our moles and convert that to the number of atoms. I like to put my units in first, lay out where I'm going to go before I put the numbers in. And so I just really carefully make sure that I'm following the diagonal rule in every case, right? Grams divided by grams cancels and gives me moles. And then moles divided by moles cancel. And what I'm left with is simply atoms. And when I set that up first with units, I find it much clearer, much more easily to plot out my course, and then I plug in the numbers. Well, step one, what's the grams to mole conversion? Here you have to use the periodic table. And underneath carbon on the periodic table, we see its molar mass, 12.01 grams in 1 mole of carbon. Our second step, we convert the moles to the number of atoms. And here's where we use Avogadro's number, 6.02 times 10 to the 23rd atoms in 1 mole of atoms. Notice that in both of these cases, the atoms get the 1, because the molar mass is the grams per 1 mole, and Avogadro's number, 6.02 times 10 to the 23rd, is the number of particles in 1 mole. So when I plug this into my calculator, I'd be sure to divide by 12.01. 2.6 divided by the molar mass of carbon, 12.01, and then I multiply by 6.02 times 10 to the 23rd because that's on top. My final answer is 1.3 times 10 to the 23rd atoms of carbon. So if you have 2.6 grams of carbon, that you actually have 1.3 times 10 to the 23rd atoms. That's how many atoms are in 2.6 grams. We're going to find out later in the semester why this is important, and we're trying to predict how much product we can expect. Calculations such as this. Let's try a second example, but let's do that in the opposite direction, and let's use an actual molecule. Let's pick a hard molecule, one where you really have to struggle to get the molar mass. Let's start with 3.00 times 10 to the 25 grams. Let's pick a compound, sodium carbonate, Na2CO3. If you've got 3.0 times 10 to the 25, I should have started, whoops, mistake. We wanted to start with molecules, not grams, of sodium carbonate. We're going to follow the same process as we did before. We're going to cancel the units that we want to get rid of. We want molecules to cancel, and we convert the molecules to moles. And then we want moles to cancel, and we want to end with grams. So if we have 3 times 10 to the 25th molecules of sodium carbonate, how much does it weigh in grams? We convert first to moles. In 1 mole, we have 6.02 times 10 to the 23rd molecules. And then we have to ask, what is the grams per mole of sodium carbonate? This grams per mole is a little more complex than we have had before. We have then the example above because this is a compound. So each oxygen weighs 16, so we multiply 16 by 3 because there are 3 oxygens. We add to that the mass of 1 carbon, 12.01 grams. And then we add to that the mass of 2 sodium atoms. 2 sodium atoms. And the molar mass of sodium is 22.99. So 22.99 times 2 equals a total mass of 105.99 grams for sodium carbonate. Now for the final calculation. 3 times 10 to the 25th divided by 6.02 times 10 to the 23rd and multiplied by 105.99 gives us a grand total of 5,281.8936. Whoa, that's a lot of sig figs. We look on our periodic, or we look at the beginning of the calculation that we have 3 sig figs here, so we need to round our answer of 5,000 and something to sig figs. So when you look on your calculator, this is the number that you see. 5,281.89, and it just keeps going. Well, in order to round this to 3 sig figs, we start from the left and we find the third position. That's the 8. So that means that if I write this in scientific notation and I round it to 3 significant figures, I need to stop at that 8. However, the decimal does not follow right after the 8, or the decimal doesn't actually happen right here. So if I put the decimal here in between the 5 and the 2, I need to move it 1, 2, 3 spaces more to the right. So 5.28 times 10 to the 3 grams represents the mass of 3.0 times 10 to the 25 molecules of sodium carbonate. Let's take a quick review of what we did. Let's go back to the top. In the first example, we converted mass to atoms. And in the second example, we went in the opposite direction. We started with the number of particles, in this case molecules of sodium carbonate, and we converted to grams. In both cases, we went to the intermediate step of moles, the intermediate conversion factor of moles. Notice that in both of these cases, moles is the top unit in the middle box. However, how we got there is different. In the first case, we converted from grams to moles and then moles to atoms, and then in the second case we converted from molecules to moles and then moles to grams. In both cases, though, we followed the diagonal rule, and in both cases we use Avogadro's number for the number of particles in that intermediate step. And that, boys and girls, is how you convert between mass and number of particles.